Welcome to another edition of Comet Algebra. This is Algebra 1, Section 1.1. Start with some definitions. The definition of the word set is a collection of objects. These objects could be numbers, could be people, anything, any group of items can make up a set. Next term is the word element. An element is simply a member of a set. And this symbol that looks kind of like a funny looking curvy E means is an element of. And if you had that funny looking curvy E and there was a slash through it, that means it is not an element of. An example using the element symbol over here, we could say that -4 is an element of the set of integers because integers does include positive and negative numbers, but no fractions. Another example here, we could say 0.5 or 1/2 is not an element of the set of integers because it does not include any fractions. All right, the next definition is called the empty set. An empty set has no elements in it. In other textbooks, I have seen this referred to as the null set, so I just thought I would throw that term in here. I very often will use this symbol for an empty set, the 0 with a slash through it. Another way to say the empty set is an empty set of parentheses. This will come up later on in the year because it's possible to have an equation that has no answer at all. Nothing would work in the equation. And when that happens, students sometimes write the words no solution, which is true and fine, but you can also use these symbols to indicate empty set or no solution. So just a quick question here to kind of explore this. Is this set with 0 in it the same as the empty set? And some people would say yes, because 0 has no value, but really this isn't an empty set. So I would have to say no here for the answer, because 0, even though it has no value numerically, it's still an element. So this set does have an element in it. So no, it's not the same as an empty set. All right, a finite set comes to an end. An example of a finite set could be -4, 2, and 12. This particular set has 3 elements, and it comes to an end. An infinite set, on the other hand, never comes to an end. For instance, if we were going to list the set of all odd integers, it would start 1, 3, 5, 7, and so on, going on forever. Now these 3 dots, we understand mean and so on. It keeps going, continue the same pattern. Your book has a term for this. They call it ellipses, but I don't know that we need to define that term, just so that we understand that it means continue the same pattern. The next 2 terms and their definitions sort of go together, the term intersection and the term union. When you take the intersection of 2 sets, you just are interested in the elements that are common to both of them. In other words, elements that appear in both sets. Union, however, when you're finding the union of 2 sets, you want all the elements in both sets. So kind of just picture yourself dumping the 2 sets together and forming the union, including all of them. The symbol for union looks kind of like a capital U, and then the symbol for intersection is the upside down of that, so kind of like an upside down U. So quick example. If we define set A to be these numbers and set B these numbers, find A intersection B, and then we'll find A union B. So first, if we were going to look for the intersection, we would want to find the elements that appear in both of them. So just kind of comparing and looking, I'm seeing that they both have a 0 in them, and they both have a 17. So only those two elements that are contained in both would be in the intersection. And now the union, we need to list all of them. And it's not picky what order you list them in. And also, if an element 0 is in both of them, you do not need to list it twice. If you did, it wouldn't be wrong or anything. It's just not necessary. So I'm just kind of going through here. Whoops, 47. Getting kind of sloppy here with my pen, I'm sorry. What else do I need? 1, 2, and 12. Okay, check my work and make sure I got them all. So again, union, all of them in both sets. Intersection, only the elements that exist in both, that they both have common. All right, the next term we're looking at is subset. One set is a subset of another if every element of the first is contained in the second. And the keyboard did not have this symbol, so it's kind of a sideways U, kind of curvy like this with a line under it. And that symbol means is a subset of. And then of course if we have that symbol and we have a slash through it, that means is not a subset of. So let's look at an example here. Set A, 1, 3, 5, 7, 9. This looks like the odd integers, the odd positive integers. And set B just has two elements in it, 13 and 27. And I'm going to put the symbol in here to ask the question, is B a subset of A? So we look here at B, 13. Is 13 contained in this set? Well, if you continued this pattern, which these three dots mean, 7, 9, 11, 13, yes. And if we kept going past 13, 15, 17, and so on, yeah, 27 is odd. So we could say yes, B is a subset of A. These next terms take many numbers in our number system and put them into different categories so we can discuss them as sets. So the first set is the set of natural numbers, and we need to learn these symbols. This is kind of a funny looking N. That is the symbol for natural numbers. I have seen in other books refer to these as counting numbers, because these are the numbers you would use to teach a little child to count. You would say 1, 2, 3, 4. Whole numbers add a 0 to the set, so it's all the natural numbers plus the plus 0. The integers have a symbol that's a funny looking Z. I don't think they use I, because later on we will use I for imaginary numbers. But anyway, integers include 0, all the positives, and all the negatives, but you'll notice that no fractions are included in the integers. The rational numbers have a symbol of kind of a funny looking Q. And the difference between rational and irrational is going to take a bit of a discussion. Rational numbers can be expressed as a fraction A over B, but just to be clear, these numbers, A and B, are integers. Should add that to the definition. Another way to talk about rationals, they are decimals that do end or do have a repeating pattern. So vice versa, irrationals, their symbol looks very similar. It's a funny looking Q, but it has this prime symbol there. So Q prime. They are numbers that never end or they never repeat. I've listed some examples here of irrationals just for our discussion. Most of us are familiar with pi. It's a number that occurs in nature. It's the ratio of the circumference of a circle to its diameter. And computers have figured this to millions and millions and billions of decimal places, and it never does repeat, and it never does end. The square root of 10. If you punch this on your calculator, it sort of looks like it does end because your calculator stops, rounds off, and just displays it as far as it can for the width of its screen. But really, any non-perfect root does not end and does not repeat. So I put root here because, like, if you entered on your calculator the third root of, say, 10, you would also get a very long decimal. 10 is not a perfect root. 10 is not a perfect square over here. So whenever it's not a perfect root, it is irrational. This example is a little interesting because it does have a pattern, but it is not a repeating pattern. So that's why it falls under the category of irrational. And this can sort of fool people because it looks like a fraction, so it sort of looks like it fits the definition of irrational number. However, you can't take the irrational number pi and just divide it by 4 and think it's suddenly going to be rational. It's still an irrational number. And then the last group we're going to look at is designated by a funny capital R, meaning all real numbers. The real numbers are all the rationals and the irrationals, everything that we've listed above. What fits outside the set of real numbers are imaginary numbers, and that is to be studied later on in Algebra 2. Now we're going to take all those sets of numbers that we just learned their definitions of, and we're going to put them on this diagram to help visually see these definitions. So this entire rectangle represents real numbers. Real numbers are divided into the irrationals, which we're just going to use the symbol Q prime, and the rational numbers, we're going to use the symbol Q. Inside the real numbers, we have a subset. The biggest subset we have are the integers, so I'll label that Z. Inside the integers, we have the whole numbers, so I'll label that W. And inside the whole numbers, we have the set of natural numbers. Now that we've labeled them, we're going to look at a list of examples here, and the directions are to place the following numbers into the smallest set to which they belong in the diagram. Let's just go through these one at a time. First, -10. -10 is definitely rational, but even smaller than that, it does belong in the set of integers. And it can't go smaller because whole numbers don't contain negatives. Next example is 5. This can come all the way down to the natural numbers. Pi, we learned, we kind of know that. That is irrational. Square root 16, that is a perfect square. And since the answer is 4, that would belong, square root 16 belongs in the naturals. 22/7 is a commonly used approximation for pi. It is not exactly equal to pi, it's very close, and we use it in calculations. But because it's just an approximation, that it's really close, it does belong in the rational numbers. Kind of a trick question. All right, square root 2, not a perfect square, belongs in the irrationals. 0, the smallest set we can put 0 in is the whole numbers. 0.7222222 repeating belongs in the rationals because it's a repeating decimal. 4/7, just a fraction, belongs in the rationals. Pi over 7. remember, just because you divide an irrational number, it still stays irrational. Now, 3.14159. Again, we use this as an approximation for pi, but it is rounded off and it does end, so it belongs over in rationals. Again, a bit of a trick question. This 0.71711711 has a pattern. However, it is not a repeating pattern. So it does belong in the set of irrationals. And last example, I believe we have a square root 6. 6 is not a perfect square, so it does belong in the set of irrational numbers. All right, I think that's it for this section. So now you have the knowledge you need to do 1.1. Thanks, good luck, and have fun with that.